Good afternoon. Today, we're going to look into a different topic, okay? And it's known as the U criteria for ductile material, okay? So why are we learning this for? In week 1, we show this example, right? So I think everything you all understand, except what is this? Maximum shear stress criteria. Okay, so I'm not touched on this yet. So I'm going to do this now. Okay, we are going to go into what does it mean to design this on the maximum shear stress criteria. Okay, so that's what we're trying to do over here. Okay, so here we go. So we are going to look at the U criteria. So there are two commonly used ductile yield criteria. Okay, so I underlined out here, this is for ductile material only. It will not work for brittle material because of the assumption that we make or this criteria make. So first of all, the yield criteria is used to determine the transition between elastic and elastic to plastic behavior of materials. Okay, so if we were to look into a stress strain curve, mechanical engineers, we are very unique. Okay, I'll tell you why we are unique. We have our strain over here, we have our stress over here, or we can have our shear strain over here and shear stress over here. We understand that the material have this sort of behavior. Okay, all right, let me draw it properly. Yeah, we understand that there's this sort of behavior. And if I draw a chain line over here, on the left-hand side is elastic, and on the right-hand side is plastic. And we are the few engineering discipline together with material science that does this, okay? In the elastic behavior, we want material in the elastic behavior for what causes? 2PO4, yes or no? 3AO3, and in future, 3EO3, right? We also deal with what? Plastic behavior, yes or no? Like what? 3CO3, remember? Right, so we are very unique. We work in both. So the yield criteria that we're going to use is to determine the transition between elastic to plastic behavior. Okay. Now, what do we mean? So the next thing you ask me, Eugene, how do you define what is a ductile material? You can see ductile over here, right? So ductile metallic. I put down here metallic because I want it to be metal. Not, I don't need to consider in the plastic materials. Have stress yield much greater than, or the stress yield is smaller than the ultimate strength, okay, for ductile material. Whereas in brittle material, or for brittle material, the stress yield is approximately equal to the stress ultimate strength. Okay. So now you know what is a yield criteria used for. You know how to describe a ductile and brittle material, metallic configuration. So there are two commonly used. So the two commonly used yield criteria for ductile material. So the first one is known as the maximum shear stress criteria. Okay. And it is normally known as Tresca criteria. Tresca spelled with a T. And the second one is known as a maximum distortion energy criteria. Okay, and this is what we call vomisis or vomisis. Okay, so usually I tend to mix up which is which. My recommendation is, can you see how Tresca is spelled? Yes or no? It's spelled with a what? T. The italic symbol that, not italic, the Greek symbol that looks like a T is what? And this symbol also represents what? Anyone? Are we clear? Just to help you remember, these are the things that help me to remember. Okay, so if I were to say maximum shear stress, you not automatically your mind will register what? Tresca. Energy will be what? Vomisis. So we are going to do both of them, okay, both of the criteria. But first of all, for today and on Friday, we are going to focus on the maximum shear stress criteria. And we have like unconsciously used this before. I'll repeat again, we have unconsciously used this before. Okay, what do I mean by that? So the stress, the shear max, okay, and I'm going to put down here from experiment. The E means experiment, which I'll write down over here, is equal to stress U divided by 2. And this is our equation number 1. Where stress Y is known as our U strength. Whenever you see anything talk about yield, okay, they are acquired by what? They are acquired from experiment, okay, and it is a what? Material property. I have a PhD degree, a student doing a PhD, that we are trying to predict the what? The yield strength. But most of the time, up to now, the technology on yield strength prediction is still what? Very experimental based. Okay. And then you will see tau max E. The E obtained from experiment. So whenever you see anything that says yield or ultimate, it's all from what? Experiment. And if you were to look back on the chart on the table, pardon me, if remember I showed you all this before, right? This is week 1 for crying out loud. Already week 1, I was planting the seed on you guys on this method. Okay. I'll let you all finish copying first. Okay. And already in week 1, what did I told you about? How to approximate your what? Your shear. Yes or no? You all could remember on week 1, we already start doing this already. So I'm going to. So this is a typical materials handbook that you can see. Now, if I will tell you this is yield strength and this is tensile, can anyone tell me what stresses is this? What sort of stress? No, what is the name for it? Think about mole circle. Which part of the mole circle does this represent? Thank you. You know that this is your what? These are your principal stresses. And if you look at the shear, right, remember, based on the what? Based on Tresca criteria, we have what? Stress or shear max is equal to stress yield divided by what? Divided by 2. So if you don't have any shear down here, right? Like over here, okay, the first one we have 250. And then we have what? 145. If you don't have any experimental platform, you just take 250 divided by 2, you get what? 125 megapascal. Yes or no? If you have the money to do experiment, what do you get? You get 145 megapascal. You want to pay time and money for just 20 megapascal? Think about it. Likewise, over here, there's another value over here. This is 150 from experiment. If you only have 10 tensile, you can use 260 divided by what? Divided by 2 is equal to what? Again, 130. Okay, so it's not so far away. I think it's a very good what? Good sense of what? Approximation. Okay. If we were to go back over here, right? These two criteria over here, the Tresca, okay, is more what? Conservative. Okay. This is more aggressive. Okay. Later on, I'll show you why. Right? Okay. So the next thing that we want to do now, okay, is we want to relate Tresca criteria. We're going to relate Tresca criteria to mole circle. Okay, we like to relate Tresca criteria to mole circle, right? So the first condition, so the first equation, or yeah, the first the first equation we're gonna look is tau max will be equal to half stress max. And this is our equation number 2. Okay. So equation number 2 is when one of the principal stress is equal to 0, okay, and the other can either be positive or negative. Okay, the other can be either positive or negative. So if I were to sketch Mohs circle, okay, so I'll highlight this. I'm sketching, they're all 3D Mohs circle. Only sketching them, I just draw one circle only. Okay, so these are 3D Mohs circle. So it can be either the Mohs circle, the biggest